So, yes. Speak to me. Okay, in this case, we have a direct flux and a quadrature flux. So we ignore the eddy current, and phi d and phi q is in phase with armature current. Now, next thing that we are going to look at is all the types of formulas that we are going to use here. The torque and voltage for DC, T direct is equal to K flux direct IA, and E is K flux direct WM. And if it operates in the linear magnetic part, then TD is equal to KI squared, and EA is K times IAWM. Now, omega M is equals to 2 pi F. Then we go to the AC excitation. We neglect eddy current IA in phase with phi D. So IA is I maximum cos omega T. Phi direct is phi D max cos omega T, and EA is K phi D omega M. And therefore, KA is also phi direct omega M cos omega T. And phi D is equivalent to your RMS value of the direct axis flux. Right. The instantaneous torque is K is KA flux direct times IA. And that becomes T is KA phi direct IA. Okay, if linearity is assumed, then K T is equal to KST IA squared. E is KST IA omega M. P mechanical is E times IA, and the torque is EIA omega M. Okay, now we can look at the phasor diagram. For AC excitation, V is IA plus or times RF plus RA plus IJ, which is perpendicular to IA, XF plus XA plus EA. Now there we are. IA is the reference phasor. Then we get IAXF and IAXQ, IARF, IARA, and EA. And if we draw from there to there, that is our voltage. And the power factor angle is between V and I. Then if we look at DC excitation versus AC, EA DC over EA AC works out to be omega M and the DC one divided by omega M and the AC part. And then there's a little bit of a derivation, and we get that EDC over EAC is 1 over cos phi. Now we get to a compensated motor. Let me just get this thing a little bit this way. Okay, compensated coil connected in series with the armature, which will produce flux in opposition to the Q axis flux produced by IA. So L effective is LA plus LC minus 2, the mutual LA and LC. LA is the inductance of the armature, LC is the inductance of the compensating winding, and M is the mutual inductance between LA and LC. There we have our single line diagram. Resistance of the field, reactance of the field, armature stuff. And there our phasor diagram. Then we have an alternative design for a compensated coil, where we have a short-circuited compensating winding. All right, let's look at an example. 120 volt, 60 hertz, 185.6 watt motor runs at 2000 revs per minute, takes a current of 0.6 amps when connected to DC source. The resistance and the inductance measured at the terminals are 20 ohm and 0.25 Henry respectively. Compute the speed, torque, and power factor when it is connected to an AC supply. So there we go. E is V minus IARA, which was 120 volts. Minus 0.6 times 20, that gives us 108 volt. XL, 2 pi FL, and there we get it is 94.25 ohms. Now, if you look at the AC side, EA plus IR is equal to V squared minus IAX squared. That gives us EA is 93.84 volts. NAC is NDC times EDC over EAC. So there the speed was 2000, and we calculated the DC voltage is 93 and the AC voltage is 108. That gives us a speed of 1737.78 revs per minute. Power factor angle, cos phi, is EA, you can see there, divided by EA plus IR, which gives us that voltage there, divide by the voltage there. That gives us that angle there. So that means it is 93.84 plus 12 divided by 120 gives us 0.88 lagging. Mechanical power is EAIA. That is 93.84 times 0.6, which is 56.3 watts. The developed torque of the direct axis torque is P mechanical over omega M. That is 56.3 times 60 divided by 2 pi and the speed. That gives us 0.308 Newton meters. And the efficiency is P out over P in, that gives us 88.9%. Now for a compensated motor, the armature winding is of the distributed type. Winding distributed in more than one slot, and the winding factor equals to the distribution factor and pitch factor. So there we have KD is the phasor sum of the induced EMF divided by arithmetic sum of the induced EMFs. So those are the arithmetic, and that is the phasor voltage. So KD is equal to 2 over pi. And ETAQ, in other words, the transformer induced EMF due to the quadrature X in the armature is 2 square root 2 times phi Q Fs Na Kw over C. So if Kp is equal to 1, then we have Kw is equal to Kp Kd, and that is then equal to Kd. ETAQ is the transformer induced voltage in the armature due to the quadrature axis, and that is 2 root 2 phi Q Fs Na times 2 divided by 2p pi. Now C is 2p induced EMF in the armature due to the rotation in the quadrature axis. And Fr is P times N, That's the induced EMF in an armature due to rotation in the direct axis field. Now, E rad is the rotational rotational voltage induced in the armature due to the direct axis. And that is 2 square root 2 phi d NA F and R over 2P. And TSD is induced EMF transformer in the stator due to the direct axis. That is 4.44 phi d Fs times Ns. Now, if we look at this equation, V is equal to IRM angle 0 plus E rad angle 0 plus IXM at an angle of 90 plus ETAQ at an angle of 90 and ETSD angle of 90. All right, so then we can say that using Pythagoras, V squared is IRM plus E rad, which is that part, plus this part IXM, ETAQ, and ETSD, the square root of both of them, and therefore we can get the power factor. Cos phi is IRM plus E rad over V. Have you got it so far?
I'm getting it.
Huh?
I'm getting it.
Okay. Now let's look at an example. Example is always easier to follow. So there we have a single phase, 2-pole, 230-volt, wave wound. What the hell did I write there? Okay, universal motor. As NS, the number of turns in the stator is 400, and in the armature is 1200, and the full load is 1 amp. Phi D is 0.8 milliweber. Z of the motor is 20 plus J30, and 50 hertz and 7,000 revs per minute. We must calculate phi Q, PD, P out, N for 230 volt DC 1 amp. So IRM is 1 times 20, and IXM is 1 times 30. That gives us 20 volt and 30 volt. ETSD, remember, is the transformer induced EMF on the stator due to the direct axis. It's 4.44 phi d frequency and number of turns. So that's 4.44 times 0.8 milliweber times the frequency is 50 and the number of turns is 400. That gives us a voltage of 71.04. The rotational EMF in the armature due to the direct axis flux is 2 square root 2 pi d FR over NA over C. So that's 2 square root 3 times 0.8. And the frequency is 7,000 revs per minute divided by 50 to give us the frequency times 1,200 divided by 2. Because C is a wave bound and therefore C is 2. That gives us 158.4 volts. And then V squared is IRM plus E rad squared plus IXM plus ETAQ plus ETSD squared. And from that we calculate ETAQ, and that comes to 44.127 volts. Now, ETAQ we have, now we want to know what phi Q is. So you just ETAQ times 2 pi divided by 2 square root 2 divide by 50 divide by 1,200 divide by 2. That gives us 817 microweber. Cos phi IRM plus E rad over V. That's 20 plus 158.4 divided by 230. That gives us 150.776 lagging. And the input power is V times I cos phi. That's 230 times the amp 1 times the power factor 0.776. That gives us 178.4 watts. PD is EI, which is ERAD, which is 158.4 times 1. That is 158.4 watts. And NDC is NAC over cos phi. So that's 7,000 over 0.776. That gives us 9,020.6 revs per minute. Okay, that covers this part. Is there any other questions that you have of the previous one? Anyone?
Sir,
Yes.
so for chapter 6, we're gonna start from 6.9
Yeah.
only. We don't start from 6.1.
No.
The rest is not the part of the syllabus.
No.
Okay, thank you.
And then the next one that we are going to do is the alternator.
So does that mean we're done with chapter 6?
Yes. There are some problems that you can do. If you struggle with it, you can let me know.
Okay, sir.
Okay. Moet versigtig wees. Okay. Any other questions?
When is the next class?
Next week, same time.
Next week, same time.
Yeah, or do you want it earlier?
No, it's fine. 8 o'clock, I think it's fine.
Okay. If then there's nothing more, then we can see you next week, same time.
Okay, thank you, sir. Bye.
Okay. Bye.